Hi guys, welcome to God Academy, and in this lesson I'll be taking you through triple dot products. Triple dot products, popularly called scalar triple dot products. In our previous lesson, I took you through cross products and you realized that cross product yields a vector quantity, dot product yields a scalar, and triple dot products yields a scalar as well. Okay. Now, what is triple dot product? So this is actually geometry. So in vectors, which is I'll call it vector geometry because it's trying to solve geometrical problems using numbers and matrices and vectors, right? It's so beautiful. Let's see what this has got to do with what you're doing. Now, a triple dot product is simply represented as A dot B cross C. It's so nice. A dot B cross C. So this is triple dot product. So I have a dot product and a cross product being combined, and that is what we call triple dot product. So if you see a problem like this is not B times C, please. B cross C. A dot B cross C. And that gives us the expression A1, A2, A3, B1, B2, B3, C1, C2, C3. This is simply finding the determinant of what a 3 by 3 matrix with A as your row, B as your row, and C as your row. As simple as that. So it said that if you find the triple dot products of any three vectors and the result is given as a scalar which is greater than 0. So if this is greater than 0, we call this a right-handed system. Right-handed system. Okay, it's so important. If it is less than 0, we call it left-handed system. Left-handed system. Take note of that. Okay. Then also, if three vectors A, B, and C given in the order are said to constitute a left-handed system. Okay, that's exactly what I was saying. Yeah, when it is less than 0, it's also important. Okay, so that is scalar triple dot products. Now, what is the essence of scalar triple dot products? Let's look at some of the inference or what we use this for. First of all is what we call the linear dependence. Linear dependence. For you to analyze linear dependency, scalar triple product is one useful thing to use. So if three vectors A, B, and C are linearly independent, coplanar. So we call it non-coplanar. They are not in the same plane or they are not collinear. So we call them linearly independent. Okay, linearly independent only if their scalar triple dot product A dot B cross C is not equal to 0. So if you find the triple product of three vectors and it is not equal to 0, then it means that these three vectors are said to be what? Linearly independent. But if it happens to be 0, then it means that they are linearly dependent. Let's look at the geometrical application of triple dot products. It's used for finding the volume of a parallelepiped. Volume of a parallelepiped. Okay, so any parallelepiped with an adjacent size A, B, and C, the volume is given as the magnitude of A dot B cross C. So it was found out that whenever you find the magnitude of your triple products, it is equal to the volume of a parallelepiped with the adjacent size A, B, and C. We can also use scalar triple dot product to find the volume of a tetrahedron. Tetrahedron. And the volume of a tetrahedron is simply given as 1 out of 6 multiplying the absolute of A dot B cross C. Take note of that. So this is the volume of tetrahedron and this is the volume of parallelepiped. Please take note of this. Now let's solve a couple of examples for you to understand this better. So the example says that use scalar triple products to show that the vectors A 1 4 negative 7, B is equal to 2 negative 1 4, then C is equal to 0 9 18 are coplanar. So we have to show that these three vectors are coplanar. What do? We simply find their triple products, and that gives us what? A 3 by 3 matrix. We want to find the determinants. So you write 1, 4, -7, 2, -1, 4. You have 0, -9, 18. Something like this, you can punch it into your calculator nicely. So plus, minus, plus, as you do, right? So I'll have 1 positive. When I nullify, you realize that, let me use blue, all this will go, right? So I'll have this. Please take note. So I'll have -1 times 18 minus 4 times -9, right? Then I'll have -4, which will be multiplying this and this. So 2 times 18 minus 0 times 4. And finally, plus -7 multiplying 2 times -9 minus 0 times -1. So what do I get? This -18, this one is what? Plus 36, right? So -18 plus 36 will give us positive 18. Then I'll have, this is 36, this is 0. 36 times 4, so minus 4 times 36. And this will be what? 18 minus 0, -18. So I'll have 7 times -18, it should be positive, or negative 7 times 8. Then you punch this one into the calculator. And what are you getting? I'm getting 18, right, minus 4 times 36, right, plus 7 times 18, and that is 0. So the answer I have here is equal to 0. Once it's equal to 0, we can confirm that indeed it's said to be hot, coplanar. As simple as that. As simple as that. Okay. Okay, so let's see another beautiful problem here. For the last, then we close chapters on triple dot products. We solve more examples later. So it says that find the volume of the parallelepiped. Parallelepiped determined by vectors A, B, and C. Now vector A is given as I plus J. Vector B is given as J plus K. Vector C is given as I plus J plus K. So what do? We extract. So A is giving me 1, 1. B is giving me, so 1, 1, 0, sorry, 1, 1, 0. B is giving me 0, 1, 1, and C is giving me 1, 1, 1. Let's draw. So A, which is what? 1, 1, 0. B is what? 0, 1, 1, and C is 1, 1, 1. We find the determinants here as simple as that. So we have 1 times what? It will cancel. So 1 times 1 minus 1, that is 0, right? Minus 1 multiplying, this will cancel everything. I'll have 0 times 1, which is, and the other one is 0 times 0. So I'll have 0 plus 1, and the answer is, so the volume of the parallelepiped is simply equal to 1. It's simply 1. Simple 1. Okay, as simple as that. So this is all I have for you in scalar triple products. I'll see you as you find equations of lines and planes.